Man, I love making 3D games in GameMaker. As many of you know, GameMaker allows you to make fully 3D games using a 3D API. Some of you might also know that making a 3D game in GameMaker is the ultimate equivalent of pain. Now, of course, that is not completely true. 3D games made with GameMaker have been around for years, and I love every single one of them. Why? Well, because they were made with GameMaker, and a handful of them were legitimately good games. In this video, I would like to show you how I use GameMaker to create 3D environments and how you can do the same. For this, I will be using GameMaker Studio 2, Blender, and Paint.net, but of course you can use any 3D modeling and photo editing software that you like. I'll also talk about writing simple shaders for your game to make the lighting look a bit more natural and maybe a bit more realistic. It's definitely possible that you won't find every part of this video interesting, and that's why I divided it into small sections which you can then watch or skip over to your liking. Well, with that all out of the way, let's get started. Hey there guys, how's it going? In this video I'm going to show you how to make cool 3D environments in GameMaker. Let's just get started with setting up a camera for our scene. As per usual, I start with this sprite created by Mark Overmars from way back in the day for our player. Create a new object with Alt-O and call it something like Object Player or something, really anything will do just fine. Click on Add Event and add a Create Event. This is where we'll be setting up our camera. We're going to add some variables for our player object here, which we will use for the player's orientation and position. We're also going to enable Z-buffer testing, which enables GameMaker to use the Z or depth buffer to correctly display 3D objects on screen. In GameMaker Studio 1.4 and older, this function is called the3D set hidden, which you can also set to true. Now let's add another event. Click on Add Event and select the normal draw event. I'm going to create 3 variables that I'm going to use for the player's 3D orientation. The face variable will control our horizontal rotation, while pitch controls our vertical rotation. I'm also going to set up 2 matrices, one for our view frustum and another for our actual projection. For this I will start by creating a view matrix where I will pass in our x, y, and z coordinates along with the 3 variables from earlier, which will control the direction we will be facing later. You don't have to worry about the final 3 vectors for now, unless you're going to do some fancy 3D tilting stuff at some point. Next up is setting up our actual projection, which is what we'll be seeing on our screen. I'm going to use the matrix build projection perspective FOV function to set up a 3D projection in which I will be able to control the field of view, the aspect ratio, and the near and far clipping planes. It's always good practice to avoid magic numbers when you're coding. Instead of writing a fixed value for our FOV, you might as well replace it with a variable. Not only is this a lot more agile, it is also a lot more readable. I will calculate the aspect ratio once in the create event and set the clipping planes to 1 and 8192 respectively. I know what I just said about magic numbers, but for these values I don't really mind that much, to be honest. Okay, so the next thing to do is actually use all this code we just wrote with our game's camera. For this we need to get the currently active camera with camera get active. We can then pass our view and projection matrices to the current camera. Don't forget to use camera apply after you've passed these 2 matrices to the current camera, or it won't actually use them. And the final thing I'll actually add to the camera is the ability to look around using the mouse. For this I'll be using a chunk of code I've been using for around 15 years, but still works nonetheless. In the step event, all you have to do is subtract the center of the screen from the current position of the mouse on your display. For this we will also use a sensitivity variable, which will then make sure that we don't go too fast or too slowly. Right after you do this for both the X and Y axis, you need to lock the mouse to the center of the screen using the display mouse set function. This works wonders, and it took me about 5 years until I finally memorized it all. Finally, I'll clamp the pitch to a range of -89 and +89 to prevent the player's neck from snapping. And that is actually it for our camera. Now, to test if everything works correctly, I'll add 2 extra lines of code here in the step event. Because our mouse will be locked to the center of the screen, we'll set the escape key to be our panic button. Unfortunately, we don't have access to the d3d draw floor function anymore, which would allow us to draw a quick 3D floor to see if everything is working correctly. Instead, I'll add a sprite to the room, which will be used as some sort of reference point. I'll use this GIF or GIF of a 3D witch I made for one of my upcoming games. Now you can simply open your room editor and drag your player into the room. The player will automatically be added to the instance layer. Now if we drag a sprite into our room editor, GameMaker will give us a warning telling us it's going to create a separate assets layer for our sprite. Click on Create and our sprite will be added to the room. To prevent our player from becoming obscured by the sprite, I'll adjust the order of the layers just a bit. I'm going to press F5 to see what our game looks like right now, and right off the bat something doesn't seem right. Luckily, there is an easy fix for this problem. In the player's create event, you can set the object's depth to a very high value to make sure everything can be seen by our projection, and this should fix our problem. Yay! Awesome! Now if your camera controls are inverted, you can fix this pretty easily by fiddling with the controls in the step event. 3D modeling deserves an entire tutorial by itself, so I won't go into detail on how to make 3D models in Blender. Instead, I'll supply you with a model I made just for this tutorial that you can play around with. I will, however, explain how to export models from Blender to a format that you can load into GameMaker. In the next chapter, we will load 3D models as vertex buffers into GameMaker, create a simple PBR shader for extra detail and reflections, and we'll create an array of structs to create our own rendering pipeline. We are going to create our own rendering pipeline in GameMaker. In case you don't know what a pipeline is essentially a list of instructions that will be processed in a particular order. In our case, it is going to be a list of vertex buffers, each with their own textures. We are going to add vertex buffers to a list with an albedo, normal, and roughness texture, all of which will be supplied in the example below. Finally, we'll add these structs to an array, which we'll then use later to draw all vertex buffers on screen when necessary. In order to load vertex buffers into GameMaker, I will use a custom importer and exporter made by Dreamer13SQ. The function we'll be using is called openVertexBuffer, which takes in a path, a vertex format, and a boolean value on whether you want to freeze a vertex buffer or not. I recommend setting this to true as it makes rendering your vertex buffers a lot faster. The project we'll be making in GameMaker will look something like this. There will be separate vertex buffers for the tiles, ceiling, flags, and metal parts. As a bonus, I'll talk about how to make 3D water reflections in GameMaker as well. I want to briefly explain how to install the exporter from Blender to GameMaker. You need to download the source code from the official GitHub repository as a zip file. Then place this zip file somewhere where you can easily find it. In Blender, go to Edit, Preferences, and then Add-ons. Click the Install button in the top right and search for your zip file. You can then install it here, but since I already did that, I won't show it here. Make sure you enable it by searching for the new plugin and checking the checkbox. To export a model, select the mesh you want to export, go to the Scene tab on the right, and click on Export VB. You can then export your mesh to a folder of your choosing. On the right you will see various vertex attributes which are very useful. For this project I will export all models with their position, normal information, color values, texture coordinates, and tangent values. Now let's go back to GameMaker Studio. Let's start by creating a new vertex format based on the format shown in Blender. When creating a new vertex format, start with vertex format begin, which will tell GameMaker that you are creating a new vertex format. Simply add all vertex attributes in the same order as in Blender. GameMaker has its own set of commonly used vertex attributes that the exporter also supports. However, the tangents are not immediately supported by GameMaker. For this, we will use a custom vertex attribute. As the tangents are a vector with 3 float values in it, we will use vertex type float3. Then for the usage, GameMaker does in fact have a tangent usage, but it doesn't work for reasons unknown. Instead, using vertex usage text chord works perfectly. And then finally, we can store our vertex format in a variable with vertex format end. We can then reference it later when importing vertex buffers. The next thing we're going to do is import all vertex buffers with the aforementioned openVertexBuffer function. Make sure all your vertex buffers are stored somewhere in your data files folder. Create a variable for each vertex buffer and initialize it with the openVertexBuffer function. You then need to specify the path to the vertex buffer relative to the data files folder. In my case, my vertex buffers are stored in an environment folder within my data files folder. The next argument requires a vertex format. Simply reference the vertex format we created earlier here. Then finally, you can choose whether to freeze your vertex buffer or not. Like I said, it increases your performance a bit, so you should definitely set this to true. Now do the same for all vertex buffers you wish to import for your environment. Make sure they have different variable names, and also make sure you are in fact loading the correct vertex buffer. We are going to add a script that turns a vertex buffer into a struct with additional attributes. Let's add a group and call it vertex buffers. We can then create a script instance and create a function called addVertexBuffer. This function will take in a vertex buffer, an albedo texture, a normal texture, and a roughness texture. We can then turn this data into a struct. A struct is very similar to a JSON object if you're familiar with those. We can later reference all attributes of a struct to draw each vertex buffer with the correct textures. In our player objects create event, I'm going to create an empty array. An array is just a simple list of objects that you can loop through later. You can create an empty array with these open and close braces. Using GameMaker's array push function, you can easily add any object to the end of an existing array. In our case, we are going to add a new vertex buffer struct to the all vertex buffers array. Enter array push and then the name of the array you want to add something to. Then within the array push function, use our own add vertex buffer function to add a struct to our array. You can then reference a vertex buffer you've imported earlier along with the textures you want to give it. Start with the albedo texture and then the normal and roughness texture. A quick tip, the sprite_get texture name is way too long to keep it readable and short, so I created a macro in GameMaker that changes the letters SGT to sprite_get texture during compilation. Now do this for all vertex buffers and make sure you add the correct textures to each vertex buffer. Now we're going to loop through our array and draw each vertex buffer in the draw event. Before we do this, we need to set up a location, rotation and scale matrix for our vertex buffers. You can do this using the matrix build function. In this case, I'm simply going to position all vertex buffers at the origin point of the room. The rotation will be set to 0 and the scale will be set to 1. Using the matrix set function, we can actually use the matrix we just created. GameMaker transforms objects with matrices using the matrix world constant. Use matrix world as your type and the matrix from earlier as your transformation matrix. We can then create a for loop to loop through our array of structs from earlier. If you are unfamiliar with loops, I recommend reading about them before you can. I'll store the current vertex buffer struct in a temporary variable that I can reference at any time during this iteration. With vertex submit, you can submit a vertex buffer to the GPU. This function takes in a vertex buffer, a primitive constant, and a base texture. The vertex buffer can be referenced from our struct using a period. Because our vertex buffer consists of a list of triangles, we will use the PR triangle list constant. Finally, we'll use the current vertex buffer's albedo texture as our base texture. Now we should be ready to play our game and oh, what the... This is probably what you'll see when running a new 3D project in GameMaker. Everything is there, but it's upside down. To fix this, you can either set the FOV to a negative value or invert the Z up vector in the projection code. And that should fix it. It doesn't look great, but the next part is all about shaders, lighting, and post-processing. Now we're going to create our first shader. You can use Alt-A to create a new shader. Right off the bat, we need to make sure our shader uses the same vertex attributes as our vertex buffer. That's why we need to uncomment the normal attribute and add a vector 3 attribute for our tangents. In the fragment shader, I'll add two uniforms which allows us to communicate with our shader in GML. The first is going to be a vector 4 array called lights and an integer value called max lights. You can set the maximum amount of lights by setting the size of the array. In the draw event of our player, you can use the shader we're writing by using shader set. You can then also add some values for our uniforms by using shader set uniform. We're going to add an array with numbers to our shader for our lights positions and maximum range. That's why we're using shader set uniform f array. I'm going to store the uniforms we just made in our shader in GML as a variable so we can reference them here later. It is also pretty easy to get the maximum amount of available lights in our scene. Since each light is going to consist of 4 values, an XYZ position and a range value, we can get the amount of lights by getting the length of the lights array and dividing it by 4. Now we're actually going to create variables for our uniforms. In the create event you can write something like u_lights followed by shader get uniform. Then enter the name of the shader you want to get the uniform from, followed by the name of the uniform in quotes. Let's do this for both our lights and max lights uniform. The next step is to create an array of lights. Each light will have a position and a range value. These will be stored as separate values which will be put into our lighting shader. Let's create an empty array called lights. Now let's create a new script with a function called addLight. This function takes in an X, Y, and Z position and a range value. This function will automatically add these values to our lights array. Let's just add a single point lamp at our own position with a range of 100. Now everything is set up correctly, however our shader is not instructed to actually do anything with these values. In the vertex shader we need to get the position and the normal orientation of the current vertex. To do this, we will add two varyings to our shader, one called VV vertex position and one called VV normal. A varying is a value that will be transmitted to the fragment shader later. In order to get the current vertex's position, I'm going to convert the vertex's position from model space to world space by multiplying its position with the world matrix. I then do the same for the normal orientation, only this time I'm using a different vector 4 with 0 instead of 1. Now add these two varyings to the fragment shader and we can use their values in the fragment shader. I like to separate the initial color from the final GL frag color so we don't have to change the GL frag color all the time. This will be our main color. Create a new vector 3 called blend color. This will be the color our main color will be multiplied with at the end of our lighting calculations. Now add a for loop and iterate through our lights array until we hit the max lights value. You can get the current light instance by creating a new vector 4 called light. Initialize this variable with the value of lights at the current index. GLSL has a built-in distance function which you can use to calculate the distance to the current light source. While usually all values in GLSL are clamped between 0 and 1, this distance function will return an absolute value that will be way greater than 1. To counter this, simply divide the outcome of the distance function by the fourth value, which is the light's range. And finally we can add a vector 3, which would be our light's color, multiplied by the distance to the light source to our blend color vector. After this, all we have to do is multiply our main color's RGB values with our blend color. This is the simplest way of creating a per pixel lighting system. Also, don't forget to set the GLFrec color variable to main color or you'll just get a black screen. With our current lighting setup, our world now looks like this, vastly different from the unlit version we had earlier. Most lighting shaders use something called n.l. This is the dot product between the current normal vector and the vector towards the current light source. The n.l calculation yields a value between -1 and +1. A negative value means the normal is facing away from the light source. 0 means the normal is perpendicular to the current light source, and a positive value means the normal is facing towards the current light source. GLSL has a built-in dot function which we will use to calculate the dot product between the current normal vector and the vector towards the current light source. To create a vector towards the light, subtract the current light source's position from the current vertex position. Also use GLSL's normalize function so you can get a value between -1 and 1. Since we only need a value between 0 and 1, we can use the max function to set a bottom value for our n.l calculation. We can then add the result of the n.l to our lighting calculation, which will make everything look like this. Of course, the lighting looks way too harsh at the moment. Real light rays tend to bounce, especially in confined spaces like these. This is why a small room isn't completely dark anywhere where there's a light source nearby. To emulate this, you would have to use ray tracing, which would take care of light bounces automatically. Since I don't know exactly how to do that, I'm going to show you a little trick I've been using for a while. Indirect lighting will always be weaker than direct lighting. So what I'm doing here is add a weaker version of our light color, which doesn't take the n.l calculation into account. The result is something that looks like light bounces. This works wonders for interior scenes. Let's make everything look better. We're going to add PBR or physics-based rendering materials to our game. For this, we're going to use the normal and roughness textures from earlier to transform our materials from this to this, all in GameMaker. We're going to add additional normal information with our normal map and surface imperfections with our roughness map, giving us a much more realistic and pleasing look. First, we need to transform our tangents into world space in our vertex shader. This is pretty easy to do as we only need to multiply our tangents with GameMaker's transformation matrix like this. While still in our vertex shader, we need to calculate the cross product between the model's normals and tangents. To make sure we're working with normalized values, make sure to normalize the normal and tangents before you calculate the cross product. Then create a new vector 3 variable and calculate the cross product between the normal and the tangents. We can then create a new transformation matrix which we'll use in combination with our normal map to fake additional detail on our mesh. This method has been in use for many years, but it still works great. That is all for our vertex shader. Make sure to pass the new matrix to the fragment shader by creating a varying mat3 and call it something like VVN matrix. In our fragment shader, we're going to add our new varying to the top here so we can use it later. Let's also add two new uniforms. These are going to be of type sampler 2D, which are 2D textures you can use in your shader. Let's create one for the normal map and one for the roughness map. In our create event, let's create two new variables for these uniforms. Instead of using shader_get_uniform, we're going to use shader_get_sampler_index, which you should always use when using sampler uniforms. In our draw event, let's use these two new uniforms and upload our normal and roughness textures to our shader. You can do this using the textureSetStage function. This will take in the uniform sampler from earlier and a texture. For this we will use the textures we stored in our struct. With all of this set up, let's use our normal map to fake additional geometry in our mesh. Let's create a new vec3 and call it normal text. We're going to read the RGB values from this normal map, but there is a problem. We're looking for a value between -1 and +1. An RGB texture has values between 0 and +1, so we'll need to convert it to the range we need. You can do this by multiplying the RGB values by 2 and then subtract 1. This will leave you with a value between -1 and +1. After this, we're going to create another vector 3 and call it normal transformed. This is going to replace VV normal in our lighting calculations. Normal transformed is going to be the normalized output of our normal matrix multiplied by our normal colors. Then simply replace VV normal in your n.l calculation with normal transformed, and you can see your normal map in action. Okay, so next up we're going to add specular highlights using a reflection calculation and our roughness texture. Let's add a new vector 3 variable called reflection color at the start. For this we also need a new uniform called camera position, as we need to calculate the amount of reflected light that makes it into the camera lens. Let's call this one U camera position. In our draw event we can pass the camera's X, Y and Z2 position. Back in our fragment shader, we're going to use GLSL's built-in reflect function to calculate the reflection vector of an incoming light ray. This function takes the 2 light vector we created earlier for the n.l calculation and the normal vector we want the light to reflect off of. Still in our for loop, create a new vector 3 called reflected vector. This will contain the normalized output of the reflect function that takes in the incoming light ray and the current transformed normal vector. We also need to create a vector 3 from the current fragment towards the camera. You can do this at the start of your fragment shader program. Create a new vector 3 called 2camera and calculate it the same way as with the 2 light vector. Back in our for loop, calculate the dot product between the 2camera vector and the reflected vector. This will determine how much light managed to reflect into the camera. Using the POW function, we can determine the size of the reflection. The smoother a surface, the less the light will scatter around, meaning smaller but more intense reflections. Let's calculate the specular highlights while also using the values from our roughness texture. At the start of our shader program, let's get the color information from our roughness texture with just a float, in which we'll only use the red channel from our texture. Then create a new float value which will be our roughness value. We will linearly interpolate between high and low roughness with the mix function, which is just the same as lerp in GML. The lower the value of our roughness texture, the smoother our surface will be. So we'll use mix 2000 at the start and 1 at the end, and then we'll use the roughness value as our interpolation value. Now all you have to do after all of your lighting calculations is to add the reflection color to your main color, which will give you some cool specular highlights. One final thing I'll talk about is post-processing effects. I personally really like using the ACES color space, which is some complicated maths that normalizes the colors on your display. I think it looks better, but of course that is up to personal preference. You can add post-processing effects by creating a new surface, setting the surface target to your new surface, and then drawing said surface in the GUI event with the post-processing shader. Again, this is all personal preference, but it's something to look into. Of course, you can also use the application service to draw post-processing effects too, but in my case I just drew a new surface. Okay, promise, last thing. The last thing I'll show you is how to make distorted screen space reflections to simulate the look of water in our pool. Full disclosure, I learned this from Thin Matrix on YouTube from his Java OpenGL tutorial, so do check out his channel for more shader related content. What we need to do is create a secondary surface called the reflection surface. This reflection surface can be pretty low res as we're going to distort it later anyway. Duplicate everything you have and create the new surface later. For the sharpest reflections you can use a higher resolution reflection surface, but for the sake of simplicity I'll just make it half size. The difference with this camera setup is that we're going to invert the height of the player as well as the pitch value. This is what we're going to project onto our body of water using projective texturing. Let's create a new water shader. In our vertex shader, let's make sure we have the same vertex attributes as the other vertex buffers. Like before, let's pass the vertex position and normal orientation over to the fragment shader. Then we're going to replace the value of our GL position here with a new variant called VV clip space, which we can use later in our fragment shader. Then set the GL position variable to VV clip space so we don't have to calculate it twice. Then over to our fragment shader, let's load up our varyings first and then use our VV clip space varying to calculate our normalized device coordinates, which we will use to project our scene onto our water. This will give us a value between -1 and 1, but instead we want a value between 0 and 1, so divide it by 2 and add 0.5 to normalize the values. For realistic water transparency, we'll use the Fresnel effect. We can calculate the Fresnel effect very easily by using the dot product between our two camera values. Oh yeah, we need to calculate the camera position again. Anyway, the dot product between the 2 camera vector and the current normal orientation. This will give a pretty cool effect that you can also use for rim lighting. Finally, I'll set the main color to a texture 2D, where we'll use our reflection surface and our NDC variable for our coordinates. Don't forget to put your uniforms here. We can pass the reflection surface to our shader using surface get texture, and this will give you a very cool water effect. I would like to thank you very much for watching if you've made it this far. I know this is only the start of making an entire 3D project in GameMaker, but if you guys like this format, I'll definitely make some more. Feedback is always more than welcome. This entire project can be downloaded for free on my itch.io page. It is set to name your price, so if you can spare me some change I would highly appreciate it, but of course feel free to download and use it free of charge. Again, thank you very much for watching, and I'll hopefully see you in the next video. Take care.